to give him the charge. Okay, so did you don't show as signed in? Yeah.
Screen. Do you guys see? Can you hear me over the audio?
Yes, I can hear you. Superb. Thank you.
Cool. Okay. And then let's do one thing real quick. Are you looking at a presentation deck?
Yes, sir.
Cool. All right. Let me do one thing. You're like super loud. You're like in my head. So
I'll put myself on mute. How's that?
no, it's fine. I just adjusted the volume. All right. So let's get cooking. Then sorry for the delay, everyone. So you do see the presentation deck, not the presenter view, correct?
Yes, sir.
Cool. All right. Thanks for coming, everyone. This is monitoring Linux performance for the SQL administrator. It was already introduced, but I'm Anthony Nosotino, consultant and trainer and founder of Santino Systems. All the fun stuff that Prashant talked about a second ago still exists. I do have an email address, so if you do have questions about the session or anything about Linux, PowerShell on Linux, SQL Server on Linux, I'd be glad to help you guys out. I'm also on Twitter. It's kind of my main way to get information out to the community, so please follow me on Twitter, and you'll find that I frequently blog, and there's a link to my blog there. So a lot of today's topics will either show up as blog posts, which they have in the past, or I'm also a Pluralsight author, and so today's session comes from a course that I did about a year ago for Pluralsight, much longer, about 5.5 hours. So I originally spec'd it at 2. I had to really talk to my editor before that course is published to get some forgiveness. I had almost a 6-hour course, but a lot of today's material is in there. If you want access to that course for free, I can give you access to that. So please feel free to email me, and I can get you a 30-day free pass. And the reason is not because I want to sell you something, but because I only have a short amount of time to talk to you guys today, and I have much more information available to you there. And I'll try to point out throughout the course today or the session today what came directly from there. So if you want that info, go ahead and hit me up, and I'll have my email again at the end of the presentation. So where are we going to go today, guys? Well, we're going to talk about performance, and to understand performance, right, and performance monitoring, we need to understand what we're looking at, right, the thing that we're observing. We're going to talk about the Linux system architecture. And then the thing that we care most about, since this is a DBA talk, is SQL Server on Linux. And SQL Server on Linux's architecture. We're going to talk a little bit about that, not too much detail there, because we really want to learn is how Linux interacts with the hardware. And then we'll go into looking at the individual system components of our system and how those work, right? And so we're going to look at things like CPU, memory, and disk, and their primary operating system constructs, processes, pages, and file systems, right? And how those things are allocated and consumed by Linux, and thus SQL Server on Linux. As we go through each one of those big buckets, we're going to look at tools to help us identify like what we want to look at, right? We're going to be monitoring, so we're going to talk about how to monitor CPU, how to monitor memory, and how to monitor disk, and where to look, where to poke inside the operating system, and talk a little bit about what's good and what's bad. And then we're going to zoom out and talk about system monitoring tools, right? Because in addition to the individual components, we care about what's going on in the overall system as a whole. Oh, and feel free to ask questions along the way too. So if you guys do have a question, go ahead and I guess, raise your hand virtually and go ahead and let me know what you want to talk about. So things that we're going to cover operating system concepts, right? I want you guys to understand how it works, right?
Hey,
I'm not just going to give
Anthony,
you a tool.
quick question, my
Sir,
friend. Do you want the questions like as they go along or towards the end of the presentation?
as we go along, that's fine.
Okay.
And I'm assuming it's okay to go past 2 o'clock Central because we had a little bit of a delayed start. Is that okay?
Yeah, I think we should be okay.
Okay. Otherwise, I'd have to get another cup of coffee and talk even faster than I normally do.
Ah.
So, thank you, sir. So we're going to talk about how it works. And the reason why is because I want you guys to understand how it works, right? If I teach you how these things work, you'll become a more general problem solver, right? You'll know like these are the conditions that I'm looking at. And if you understand how it works, you can solve your own solution for that, or develop your own solution for the problem that you're trying to solve. We're also going to look at tools and how to view performance data, right? We need to know there's this new universe of Linux that SQL Server runs on. What are the tools that we use, right? And what do we use before from a Windows standpoint? And we'll do a little bit of comparison of what we use in the Linux world. And we are going to talk about a little bit about what's good and what's bad. Like what are the tipping points from a performance standpoint on when things start to get wonky. We're not going to cover SQL Server internals too much, and we're not going to cover performance troubleshooting. I'm not going to tell you how to fix anything. I'm going to tell you where to look so you can fix your own things. So let's move into the Linux system architecture. And at the fundamental root of it all, the operating system does one thing, right? It controls access to hardware, right? Those physical resources, CPU, memory, and disk, right? Those things that are inside our computer that we need to leverage to get the work done for our programs. Now, the thing that controls access to those resources, whether Windows or Linux conceptually, is this thing called the kernel, right? Its primary function is resource management and access, which is a really fancy way of saying it literally controls access to the hardware. Now, the primary way that it represents hardware, right, the primary operating system constructs are processes, pages, and file systems, right? So if I want to schedule a process, well, that's how I get access to the CPU. If I want to have access to memory, well, that's going to be allocated via what's called a page. We'll talk a lot about each of those components individually today. Now, above the kernel, we have this thing called the shell, right? And this is where we execute our programs, whether if I'm sitting at the command line interface typing away, or if I'm a network daemon like SQL Server, right? The shell launches my program starts executing. Now, when my program's executing, it does need to interact with the kernel to do stuff, right? To access physical resources. And it accesses those physical resources via what's called the system call interface, right? And so that's our interface into the kernel to ask it to do work. Our programs execute system calls. Those system calls do things like start new threads, allocate pages, read or write from a file, right? And that all happens via system calls over the system call interface. And at the top of our Linux architecture is us. And what do? We do what we do as end users. We cause problems. Now, there's two terms I want to throw at you right now on the left here, kernel space and user space. When a program is executed in user space, that means it's doing the thing that I want it to do, right? It's calculating the average. It's summing the results of something. It's doing work that it needs to do or computation to move my program state forward to get the work done that I care about getting done. When a program transitions into kernel space, it's doing work to really kind of facilitate the execution of that process, meaning like it's asking to schedule a thread. It's asking for more memory. It's asking to read or write from a file. So it's really not doing work to drive the program state forward, but it's doing the work inside of the kernel to get the resources to do the work that I need it to do. So as DBAs, we're probably familiar with the concept of SQLOS, right? We just learned about how Linux is an operating system that controls access to hardware. Well, guess what SQLOS does, right? It does something very similar. And we have four big buckets here across the top. Scheduling, right? Actually doing work. Sounds familiar to what we just talked about. Synchronization is another big bucket that happens inside of SQLOS, which is controlling access to system resources. I/O, anytime I need to do something on the network or disk, well, we need to do that through SQLOS. And of course, memory management, right? It's another big function of SQLOS, allocating memory to various system objects and caches and things like that. Now, SQLOS sits on top of, I guess, the operating system, you would say. It's part of the core components of SQL Server, right? Because it's the thing that needs to access or allocates the resources for SQL Server to do its work. Well, it's interesting because there was a lot of research, or there's some research back in the day by both Slava Oaks and Michael Stonebreaker, those two links I have at the bottom there, where they developed two papers and they've developed the techniques around developing operating system support for relational database management systems. And that's really the primary function of SQL OS, right? Is resource management specific to relational databases, right? So we have what's going on inside the operating system, but we also have what's going on inside of SQL OS, right? And that workload specific operating environment to allocate system resources. So by now, we've all seen this diagram a ton of times, right? How it was pulled off, right? How SQL Server wound up on Linux. And we're going to zoom in on a particular part of this in a second. So we know, right, that inside the middle there, right, that software isolated process is really a Win32 binary that's executing inside of this thing called SQLPAL, right? And what SQLPAL does is it takes those Windows system calls that SQL OS would normally dispatch out to Windows and maps those to Linux system calls, right? You see ABI calls right there, and it maps those into Linux system calls, which are executed by the host extension. And those are the things that go and interact with the hardware. So it's important to note, right? Inside Win32, outside is a Linux process. So I also have another diagram which comes, it's a higher resolution version that I drew up myself, but it comes from this blog post on how it was pulled off in SQL Server on Linux. And I want to talk about the difference between performance sensitive code and all of the other code that's executing inside of SQLPAL, right? So there's this concept of Win32 hosted APIs or library or libOS and SQL OS APIs, right? Basically differentiating between compatibility and performance. On the left, we have compatible code that's executed by the library OS, which then turns into SQL SV2, which then turns into host extension calls, which then turn into Linux kernel system calls. And then on the right, the SQL OS API, those performance sensitive code paths, things like disk IO and network IO that go through a different code path that execute into the host extensions and then out into the Linux kernel via system calls, right? So two separate paths there, but really serving the overall compatibility and performance of the system. So host extensions, right? Those things at the bottom, kind of the glue between SQLPAL and the underlying operating environment. Well, inside of there, we have a call mapping table, which exposes Win32 API-like semantics to SQL OS. It maps those down into Linux system calls. If you literally take a debugger and attach it to a SQL OS process, you will see Linux systems calls executing, and you'll be able to sift those off and be able to do some deep dive performance tuning and understanding of what's going on inside of SQL Server on Linux. Now those ABI calls, right, the things that are mapped from Win32 to Linux system calls, well, guess what they do? They do things like memory management, threads and scheduling, synchronization privileges, primitives, and also network and disk IO. Well, basically anytime SQL OS, right, has to reach out into the hardware, right? And that's the primary function of the host extension, is managing the transition from SQL OS inside of SQL Server out to the underlying operating environment. And we care a lot about this because it's more code, right? We're doing more work, or not, we're not doing more work, SQL Server is doing more work. So I'm gonna let you in a little secret. A SQLPAL is virtualization, right? Well, I've studied virtualization academically for a long time, and it falls into a class of virtualization called process virtualization, not machine virtualization. We're not emulating CPU, disk, and memory. What we are doing, or we, the product team has done, is presenting another environment inside of a process, right? That execution context that's different from that of the underlying operating environment. And so you would think that there's going to be performance penalties associated with this emulation. Well, there's not, right? Well, I would say there's not, but this thing is purpose built for SQL Server. And so the execution paths and the things that are working inside of SQL Server on Linux perform really, really well, right? This isn't general purpose. This thing is built to make SQL Server fast, or SQL Server on Linux fast. But that leaves us with this hybrid thing that we need to understand, right? Where it's Win32 on the inside and Linux on the outside. And so it's going to come down to that we need to understand resource allocation and management inside of SQLPAL. We need to understand how that turns into Linux operating system performance. And it also has an influence if you're a hardcore performance tuner on debugging, right? And we're going to talk about the first two bullet points pretty much for the rest of the talk today. But debugging, let's take a second to look at that there. What you might be used to doing as a hardcore performance tuner is attaching a debugger to SQL Server and following a code path. Well, it's a little bit different inside of SQL Server on Linux because of that Win32 Linux hybrid that we talked about. You really can't follow a code path between two different program executable types, right? In Win32, you have what's called a PE executable. And in Linux, you have what's called an ELF executable. And literally the binary program structures are different, such that when we trace those programs, there's a little bit of a disconnect. If I was tracing a thread from the Linux operating system up into that Win32 exposed environment. Now, Microsoft has some tooling to do this on their own. Some great engineering has occurred, and they have the ability to do that, but that's not publicly available to us today. So with all of that behind us, the SQL and Linux architecture and the Linux architecture, let's talk about CPUs and their primary operating system constructs, processes. So what is a process? Well, what a process is executing program code. It's an executing program, the program code, the memory allocated associated with that process, and any resources. So things like file handles or files that are open, or network sockets, anytime any network socket that's affiliated with the particular process. Now that process, we can also have what's called a thread or a lightweight process or LWP. You'll see that acronym sometimes. What a thread is really an execution context inside of a process and has shared access to the resources of a process. So I can have many threads executing concurrently on a memory space from a parent process. And that's how I'm able to really drive the concurrency of the system and get a lot of work done. Now, let's talk about process and thread creation for a second. On a Linux system, we have this concept of fork exec, and those are system calls, right? Where a process will come along, and when it's asking to create a new process, it'll fork another process, which yields a child process and its own independent process ID, and then links those two together in a parent-child relationship. If that destination process that's getting started is a different process, it'll exec the binary for that new process and load that program, and it'll start that secondary process, and it'll go off and running. That parent-child relationship still stays. We also have a concept of cloning, which is how new threads are created, and those are created within the same address space. Very cheap, very fast to create. And when we get into the presentation or the demonstration portion of this, you'll see the relationship of parent-child relationship. We'll also look at full processes and threads together. Now, what's interesting is that parent-child relationship that's built between a process that's the creator and the createe develops this parent-child relationship, and its hierarchy persists for the duration of that process. So if you kill a parent process, all the child processes go away, and we need to understand that from a process management standpoint when we're going through and working with our system. So let's take a second to look at process states. When a process is up and running and doing work and it's on the CPU and it's getting things done, that process is running. When it's running, it can transition into another state called sleeping. And there's a couple of reasons why a process would go from running on the CPU to sleeping. First off, it could be asking for something, right? Like network IO or disk IO. And if that's the case, it's going to transition from sleeping, and it's going to wait until that IO is complete. Once the IO is complete, it's going to transition into the runnable state, and it's going to get back into line for access to the CPU. Now, another reason why it can transition to sleeping is it exhausted its quantum. So very similar to SQL Server, threads have a calculated length quantum, where SQL Server has a 4 millisecond quantum. Linux has a calculated quantum length based on the interactivity and the scheduling that the system is under at that point in time. And so it's based on certain conditions. So quantum exhaustion is another reason. Now, the next reason why you go from running to sleeping is could be preemptive. Now, it's different than SQL Server, which is a non-preemptive scheduler. Linux is a preemptive scheduler. So another process more important than me could come along and bump me off of the CPU. Now, in all of those conditions, I'll transition to runnable, right? Whether I'm waiting on IO, I got preempted, or I've exhausted my quantum. Once I've exhausted my quantum, I'll immediately go back to runnable. Once if I've gotten preempted, I'll immediately go back to runnable. And once my IO is ready and given back to me, I'll immediately go back to runnable. Now it's up to what's called the scheduler to pick who's next, right? There's a line, I give a line in a queue. Even though I'm in the queue, the scheduler will come along and pick a process that it thinks is the most appropriate to get onto the CPU next. Once it's onto, it picks that process, it puts it back onto the CPU, and then I start doing my work again. And there's schedulers per core, right? So if I have a 4-core system, there's basically 4 queues and schedulers that are doing the work to get those things back onto the processors. Now, when I'm done and I'm finished doing my work, I transition to a stop state. I'm done, I'm complete, and I have a nice day. There's also another state that I transition into called a zombie state. And generally, you're going to wind up in a zombie state if something is wrong with your code. There's usually a bug and something bad happened. I put SQL Server on Linux into a zombie state when I was doing some testing, when I was developing a session. When I put it under extreme memory pressure, I caused a memory starvation issue that must have hit some sort of exception inside of SQL Server on Linux, and my program went into a zombie state. You'll see that in your process listing as defunct. And what happens is you'll become unlinked from your parent process, linked to the process ID 1, and you will basically just sit there until your system reboots, consuming those resources in a zombie undead state. So we already talked a little bit about thread scheduling, but let's do it in a more formal context. I touched on it just a second ago in a previous slide. The unit of scheduling is a thread, right? So each process will have at least one thread, and the thread is the thing that gets thrown onto the CPU to do the work. The scheduler in Linux, there's many different schedules that you can choose from. The default scheduler on Linux is called schedule_other or schedule_normal, and these are the characteristics of that scheduler. It's a time-sharing scheduler. It's preemptive, which we talked about a second ago. It's the ability of a higher priority process to come along and say, I want access to the CPU now, get back, you'll get back in line. It develops what's called a dynamic priority list based on niceness. Niceness is an external priority that administratively I can assert upon a process. I can say that this process is less nice. I'll give it a negative value, make it less nice than the other processes, and it'll get more aggressively get onto the CPU. That niceness gets put into what's called the part of the calculated priority that goes into basically choosing who's next, right? So there's an internal priority and this external priority that's exposed called niceness. Both of those go into influence what the scheduler can do. There's a calculated quantum length. Again, that's also based on priority, and it's also based on the type of process. So if you're a process that's been alive for a long time, consuming a lot of CPU, what'll happen is the scheduler will realize that, and it'll start giving you longer runs on the CPU to get your work done. But it'll pull you off periodically to keep the interactivity of the system up. Now, so there's some there's a couple tuning attributes that are published by the product team that influence the scheduler and the decision that it makes for database workloads. And I advise you guys to go ahead and check those out. They're published on docs.microsoft.com. The scheduler is also NUMA aware, which means if I'm a thread and I have a bunch of resources allocated on a particular NUMA node, my thread will get scheduled back onto that same NUMA node over and over again. One of the suggestions from the product team is to turn off this thing called NUMA balancing, which is the ability for a thread to move to another NUMA node under certain conditions. In this case, we want to turn that off because we want to keep those threads physically threads local to the memory that's allocated in the NUMA nodes that they are working in. Yep, there we go. Okay, so let's talk about what to look for on processors. So now we know how scheduling works and the life cycle of a process and how those can influence things. Let's talk about some of the characteristics that we want to look for on a Linux system for CPU. Generally speaking, I make the joke percentage of what? Like what's percentage 100% CPU utilization? I don't really know what that means, right? How does that represent the actual workload that's executed on the system? Is work getting done? If work's at 100% and all of my work is happily being processed, is that okay? Perhaps. But I like to focus on a value called load average. What load average is an integer value that's calculated on 5-minute, 10-minute, and 15-minute intervals, right? And those are weighted averages over time, where I can get a feel for how saturated or how much work my system is doing at that point in time. So what load average is that integer value that represents the run queue length plus IO weights. So it's the length of those processes that are in line to get onto the CPU, and it also adds into the value IO weights. And that kind of makes sense, right? Because remember in that triangle that we had of the process lifecycle, one of the reasons I get kicked off to the CPU is if I need to go do something like get IO, network or disk, and I'll transition into a sleeping state, and then I'll get back into the running state. So it's really taken into account whenever a process isn't on the CPU. And so if I have a long run queue and lots of weights, this value will start to creep up. What's a bad value? You generally want to see a value of 1 or less per core. So if you have a 4-core system and you're running at 4, well, you know you're at the capacity of the system. And so that's an integer value load average. And we'll look at that in a little more detail in a second in the demo. Spikes aren't bad, right? If a system peaks up in utilization for 10, 20 seconds, is that okay? Probably. Did it come back down pretty fast? Yes. And the duration of that spike, well, is it bad because you have an interactive workload and things slow down for 20 seconds? Maybe. And that goes down to the baselining and understanding your workload. And really, I just want to highlight that load average gives us insight into these quick bursts in utilization because it represents its data in 5-minute, 10-minute, and 15-minute averages. So we can really see, is something occurring right now? Has it recurred over the last 10 or 15 minutes? And I can then get a good feel for what's going on and then look deeper into the performance of the system. The other thing that we want to concern about is any waits, right? Anytime there's long waits for either for user, for IO, for system, those will all influence the system and transition a process out of the running state into a waiting state. So what are some of the tools that we use for process monitoring on Linux, right? You guys are probably, as Windows DBAs, you're probably used to using Task Manager and things like that to get a point-in-time view of what's going on in your system. Well, the analogous tool in the Linux world is Top, and another tool called HCop. Top comes with every Linux distribution. HCop is a third-party tool, and I'm going to show it to you a lot today. I highly suggest looking at HCop as your primary process monitoring tool. What Top and HCop will do will give you all of that core system information, both CPU, disk, and memory, in a auto-refreshing view. It's very similar to Task Manager, so it refreshes every 2 seconds, so you can see what's going on. PS, or Process Select, is the ability to do that same analysis for the process listings based on what they're consuming and the resources that they're working with, but at a particular point in time. It's going to spit it all out to the console, and then you can analyze that without it refreshing automatically for you. Now, if I want to go a level deeper and I'm going to look inside of a process and I want to learn what's going on, I'm going to use two tools called MPStat and PIDStat. If I need to know if a process is spending a lot of time in kernel mode versus user mode, these are the two tools that I'm going to use to help me discover that. Both of these tools do significantly more than that, and they're going to show up throughout the presentation today, but we're going to that's their capabilities from a process standpoint. It has a lot of functionality in I/O and also memory management, which we'll talk about in a few minutes. DStat is what I call the monitoring Swiss Army knife. Pretty much any monitoring capability that you would need on Linux is available inside of DStat. I don't cover it today from a demonstration standpoint, but I do cover it in my Pluralsight courses if you guys want to dive into that. DStat's a fantastic utility. Pretty much, like I said, the monitoring Swiss Army knife to get what you need out of your system for point-in-time monitoring. Now, all of this data, right, that feeds into Top and HTOP and PS and all of these utilities comes from a thing called ProcFS. What ProcFS is a virtual file system. So literally, it's a directory in a Linux in your Linux file system that exposes the current running state of the kernel, right? So it's going to show us all the processes available in our system. It's going to give us the memory layout. It's going to give us the processor layout, and any kernel configuration is all represented inside of ProcFS, right? And so that's essentially the running state of your system, your kernel, exposed as a file system. And so tools like Top and HTOP will go and read the data that exists inside of ProcFS, and then that's how it gets its information. And we'll go look at ProcFS in a second together during the demo. So we're going to look at processes and threads. We're going to look at how to identify those on a running system. We're going to look at load average on a system under pretty extreme CPU saturation. And we're going to dive around inside of ProcFS. So let's go ahead and switch screens and get started. So here we are. I'm using Bash on Windows, and I've already SSH'd into a SQL Server on Linux VM that's running on my system here, and I'm going to launch a utility called HTOP. Now, what HTOP is kind of that task manager view of the world, right? So here on the top left, you can see the per processor utilization for each of the 4 processors that I have in my system. We can see that I've allocated about 8.95 gigabytes of memory out of a total of 11.6, and no swap is being consumed. On the top right here, you can see I have 52 full processes running on my system, 208 threads, and one process right now is actually in the running state. We can see my load average in 1 minute, 5 minute, and 15-minute load average or averages, right? And so right now we can see my load average is very low, right? I'm literally doing no work, right? And over the last 5 minutes, a very, very small amount of work, and a small amount of work over the last 15 minutes. We have uptime here as well. Now in this listing down here, we have all of the currently I don't want to say running processes, but all the currently existing processes on my system, sorted by process ID, right? There's a unique identifier for each and every process, the current process's owner. We have that internal dynamic priority, which is a value of 20, so everyone is equal. And we also have an external priority or a niceness of 0, so everyone is an equal resident in the scheduler in the sense of priority. We have our virtual address space and our resident set size. So this is the amount of virtual memory allocated to an individual process. The resident set size is the amount of physical memory allocated to this process at this point in time. Any shared memory, that's what we have in the SHR column. And then the current state. These are all sleeping. It'd be kind of hard to find a running process with this few things happening at this point in time. This is the percent CPU utilization for each individual process and what it's contributing to the overall utilization on the system. And then also the percent memory allocated, and then the amount of time the process is spent on the CPU, right? The amount of time it's spent doing work. And then finally on the right here with the actual process. Now this listing over here is sorted by process ID, but it's also sorted by with the ones that have a parent-child relationship. So let's go ahead and scroll down and find SQL Server for you guys. And there we see a bunch of SQL Server processes. We have the original process that boots up of SQL Server, right? And that's kind of I've been told, a watchdog process that then starts the actual SQL Server process. And so that's the second process you see there. And these are full processes, right? Because they each have different process IDs. And there's a parent-child relationship between those two because of how they were started up and the system calls they use to launch the new processes. We then see a bunch of threads. We can tell those are threads for two reasons. One, that they're shaded green, but two, because the memory space is identical, right? They're sharing the same memory space. So 10.4 gigabytes of virtual memory, 8.7 gigabytes of memory that's physically resident in memory at this point in time. So 74% of the system memory is allocated to these processes. So it's not that each process is consuming 10 gigs, they're sharing that memory space. When I booted up my system, I went ahead and I have a large table inside of my SQL Server on Linux system, and it's about 9 gigs. And I just did a select star on that table and to load all of that into the buffer pool. So that's why we have this big allocation here. The max memory for my SQL Server instance is 8 gigs, right? So I intentionally have that table as a little bit larger than the maximum memory that's available inside of my Linux system, which is going to show up in the next demonstration that we do on memory in a second. Excuse me. So let's start a demo here. I'm going to jump to a different terminal. I'm going to switch terminals here. And I have a program called MySQL CMD. What that will do is that it creates a SQL CMD connection to my Linux machine, and it does some work. And what do I want it to do? Well, I have checkDB in a hard loop inside of that file. Basically, this just saves me from having to type my password during this demonstration. So what's happening behind the scenes is I'm executing checkDB over and over and over again on my database on my SQL Server on Linux system. So I'm going to jump back to this console here and launch HCop again. And now we're going to see a different picture, right? Stuff's happening, right? We're doing work. And so our system, we know, has 4 processors in it, which means when I'm running checkDB, I'm going to get about 4 threads that are doing the majority of the work. And so now if we look up here, you're going to see that's going to oscillate around 4 based on what's going on. So we can see 4 running at this exact point in time. On the left here, we see red and green, right? Green is user time, right? It's a time spent doing work to drive my process forward to get its job done. Red is kernel time, right? Because what's happening under the hood is every once in a while, this process has to wait because that table that I created is bigger than the amount of memory that SQL Server could hold in a buffer pool. So I'm driving disk I/O intentionally for this demonstration so we can see the difference between the two. So we're doing work, but we're spending a lot of time doing I/O and supporting the process in kernel time. All right, so let's kill that demo and get back over here. And while we're over here, I'm going to switch over to super user for a second, because now we're going to go and slide and look into procfs, and we're going to look in what's going on in there. So if I go into procfs, it's in the directory /proc. Gonna press enter, and we'll do a directory listing instead of there. So here we see a bunch of data. Those directories on the left, there's numbers. So you see number 1, number 14 or 1148, 1454. These are this is a directory for each process that's currently existing on this system. On the right over here, we have things like CPU info. We have, I believe, mem info, things that represent the current running state of the kernel, right? So what the CPU topology looks like, what the current memory topology looks like. So lots of information available to us instead of here. So if I do something like lscpu, which is the command to list all the processors on my system and their attributes, which you can see here, I have a single core 4-socket machine. If I go and I look at CPU info, which is just the contents of that text file, it's gonna look eerily similar, right? Because this is literally where these programs get their information from.
Hey, Anthony, there are a couple of questions here. Paresh here.
Shoot.
So one of them is by Alvaro Costa. And the question is, since SQLPAL is process virtualization, would SQL on Linux be penalized after applying OS patches to fix meltdown?
Awesome. Let me sorry, I'm just getting over the flu, so I have to try to mute the cough. So actually, I think it's the other way around. I think SQL Server on Linux would actually benefit, right? This is totally like theoretical. I have no hard data to back me up yet. But one of the main reasons, or I guess design tenets, you could say, behind SQLPAL is to keep a process in user mode as long as possible, right? And that's the thing about the Meltdown Inspector vulnerabilities, is that the patches now have taken the page table entries and separated them into kernel and user space, right? And so we have an issue with TLB flushes that have to occur as we switch those page tables in and out. But that's during the transition between user time and kernel time. Now SQLPAL, right, that's where the engineering is. How do we keep this process in user space as long as possible? And we're going to talk about that specifically in the memory section and also the disk I/O section. I'm going to talk about some of the optimizations that have been done that will allow the process to stay in user mode for a longer period of time. Awesome question.
And one last question. HCop is a SQL Server related command or a Linux command by F. Puma?
It's a Linux command, right? So generally speaking, people use a command called top. Top's available in every Linux distribution. But what you see is there's a lot less information, and it's encoded a little more in a more challenging way. Like I don't have the pretty colors and things like that. And so we have a lot of the same info, right? We have our uptime, our load average is available here, number of processes running, number of sleeping in different states. But for me, HCop has always been the go-to monitoring tool because of the way that it represents data, and I can get a little bit more out of this a little faster, the ability to sort and build process trees and things like that. It's a third-party utility that's installed simply by doing a yum install HCop, right? And that'll allow you to install HCop. I'm glossing over the fact that you have to add an additional repository. So actually you have to do this. You do yum install EPAL release. That'll install the EPAL repository. And then once you do that, you can do a yum install HCop, and that'll install that utility for you.
Cool, thanks.
Cool, thank you. Okay, so we looked at CPU info. Okay, so we looked at this stuff, right? We looked at CPU info, the file specifically. Now I want to take you into one of these directories, but which one do I want to go in? Well, of course, we're going to go into SQL servers, right? Now, how do I find the process ID for SQL Server? Well, I could scroll up and down in the list inside of HCop, or I could use PS and try to find it that way. But a better way is to use a program called PIDOV, and I type the binary name, SQL Server. It's going to tell me all of the process IDs on this system that have that match that string, right, for SQL Server. And we see two, right, 1132 and 1554. Well, we saw there was like a bunch of processes and threads when we looked at it in HCop, but there are two full class actual processes, right? The rest of those were threads, and there's two. Well, which one do I pick? The first one, 1132, is the one that starts up or bootstraps SQL Server on Linux 1554 is the actual process. The second process is the one that's actually going to do the work of SQL Server, right? Like I said, it's my understanding at 1132, or that first process is kind of a watchdog process that bootstraps the system. Now, we go inside of 1554 and we do a directory listing in there, right? We're simply in the directory. We're in this directory /proc 1554, and the contents of that directory are now the running state for this individual process. So inside of here, I have a ton of information that represents the current state of what's going on inside of this individual process. And this could be any process on the system. I'm just picking on SQL Server because that is what we'd like to talk about. So inside of here, if I do a directory listing in a different way, I use an ls-la, we can see there's a ton of information here, right? Just even looking at the links, we could have the current working directory, which is a link to var opt SQL. The current executable is opt MSSQL bin SQL Server. Tons of information available to us just simply by doing that. Now there's a lot more information also in here, things like our file descriptors. Any file that's opened by SQL Server on Linux is going to be exposed to us inside of there. If we go and look at this file here, status, we're going to look more as a command that will expose the contents of a file. If I go into here, I can get even more information about the current running state and the memory profile of my process. And so here we know it's SQL Server. You can see its current state, right? It's thread group ID 1554, it's process ID 1554. Let's jump down and look at this, some memory accounting information. We can see our virtual memory peak, or the largest amount of virtual address space allocated to this process, the current allocated space, any locked pages, any pinned pages. Hardware is the peak resident set size, and then the current resident set size. So the most physical memory that this thing is consumed is this 9 gigs right here. The amount that's mapped in what's called anonymous pages, which we'll talk about in the next section, and file map pages.
Quick
Data
question
pages,
for you though.
sir. Yep.
So after we run check-db, amount of memory of SQL Server was reduced. Is it a correct behavior? This is by Vyacheslav Sherbak.
So when you're saying when you ran checkdb, the memory allocated to the SQL Server process went down.
Yeah, that's his question.
I'd have to look into the details of that specifically. I haven't observed that on my own, but we can try that here in a second too, if you want to.
And somebody has recommended, Carlos Robles has recommended that nmon is also another good monitoring tool for Linux for this.
Cool. I'll have to check that out. So thank you. So these are the kind of the big bucket memory accounting things, and we're going to look more closely at those in a second. So let's jump back into the presentation and talk about some more stuff. So what we did so far, right, was we identified processes of pages, right, or threads, and differentiated between the two. We looked at load average, right? We spun up that CPU workload, and we saw that our load average was increasing. And then we also looked at inside of procfs, right, what's going on inside of there. Let me do one thing before we move too far. Yeah, I did kill that. Okay. I want to make sure that that workload's not still working. So let's move into memory and pages. So memory. Inside of Linux, the memory layout and architecture is similar to that of most modern operating systems, right? We use virtual memory to represent the process address space inside of a process. And it's the responsibility of the operating system to map virtual memory back to physical memory. So those virtual pages are literally mapped to physical pages, right? And that's where that whole concept of page table entries and things like that comes into with what's going on in the news right now. Each of those pages, each of those pages are available, or the memory allocator inside of Linux is NUMA aware, and it maintains a free list per node, right? So as I'm allocating pages to a process, I'm going to allocate those to a process that's, I'm going to allocate those from a list of pages that are physically adjacent to the process that's executing on a particular NUMA node. Pages, that the page is the unit of allocation for a particular piece of memory, right? So I'm going to allocate those things for a particular process. When a process is responsible for its own allocation, those pages are classified as what's called anonymous, right? And so SQL Server on Linux does that, right? It uses its own allocator called JEmalloc to go and ask the operating system for a page and does that accounting internally. Those pages are classified as anonymous. So we looked a second ago at the memory accounting information for SQL Server on Linux. The majority of those pages were classified as anonymous. It's not that they're unaccounted for, it's that there's someone outside of the kernel that's responsible for tracking that information. Memory is the paging algorithm inside of Linux is called demand paging. So what happens is in a virtual address space, if I go and I need to access a particular memory location, if there's not a physical page behind that page, then I have to go out, get it, and stick a page there, right? So access to physical memory, if nothing's there, well, I have to go get a page and put it there. That's called a minor page fault, right? Where that page wasn't actually allocated underneath a particular memory location. Now, a little bit nastier is what's called a major page fault. What happens there is the memory that backed the physical page was written out to disk, right? So when I go and I access that virtual memory space, if I have to go out the physical disk, allocate a page, copy the page from disk to the newly allocated page, and then read that memory, that's called a major page fault. And there is a significant amount of access latency associated with a major page fault. Now, you have to ask a question, why would a page be swapped out to disk? Well, there's two primary reasons inside of Linux: time and pressure, right? What's going to happen behind the scenes is the kernel will scan pages, and if you haven't been used in a long period of time, it'll take that page, write it out to disk, and take your physical page and throw it back onto the free list for someone else to use, right? It's basically saying, I know you're not using this for a long period of time. The buffer pool, it can be in that condition where it's going to be sitting in memory for a long period of time. So that's something that we do have to look out for, that the kernel isn't going and swapping those things out behind the scenes on us. Another thing that we have to look out for is memory pressure. If we have a process that comes along, like right now, we're at a tipping point, right? If you saw the memory allocation on my system, we were at about 8 point something gigs allocated across 11.6 total. That's a lot of memory. If something needed to come along and allocate 4 or 5 gigabytes of memory, well, it would have to start taking memory from other processes, right? And it'll start swapping those back-end pages out the disk and allocated a new memory to the new process that came along for allocations. That memory pressure can put us in a bad situation on our system, causing tons and tons of major page faults. And we're going to look at that very closely in the demos here in a second. There's another type of memory on our system, or another memory consumer on our system, and that's called the file system cache. Basically, any unused or unallocated memory on our Linux system will be allocated to the file system to really help with the interactivity of the system. So file metadata and file page data will be stored in the file system cache, right? And this is the extra memory that's just kind of hanging around on our system, helping the interactivity of our system by giving that to the file system. So it helps out with our disk latency, right? Now there's a concept called swappiness. What that means is it's how fast the operating system will tip over that file system cache and take those pages and give those to a user process. And that's one of the things that the product team suggests that we change in our Linux system. If you follow that link there, there's a deeper dive information, some deeper dive information on swappiness, the default value being 30, which is a kernel parameter. The product team suggests changing that to 10, right? Because a relational database system generally isn't going to be something I'm going to be operating with very interactively at the command line, that I want those pages to be available to user processes, in other words, SQL Server, to get work done.
One more question for you, buddy.
Shoot.
So he's saying that is via Cheslav. Is SQL Server on Linux support CLR libraries? If yes, how about performance? Where CLR functions work better, Linux or Windows?
I don't know about CLR libraries, but let's track that question and we'll definitely get back to you on that one.
Okay, cool. And just check off time. It's about 2 minutes past the top of 3 or Eastern time. So.
Cool. Yeah, at this rate, we're looking at like 2:20, maybe 2:30 at the latest. So.
Okay.
Yeah. So regular pages, right, are allocated in 4K chunks. We know this is memory pages. We know data pages inside of SQL Server are 8K, right? So I'd have to have literally 2 physical memory pages allocated for each individual data page inside of SQL Server. So one of the questions about Spectre and what's the other vulnerability? It's not coming to my mind right now. So with the CPU bugs that are available, one of the things that people are concerned about is TLB cache misses, right? Being and switching between kernel page table entries and user page table entries. Well, transparent huge pages will actually help us a little bit with this. So SQL Server on Linux, or just Linux in general, supports this thing called transparent huge pages, where I'm going to allocate memory in 2 meg chunks instead of 4K chunks. So I can represent a larger physical space in memory with one logical page, right? So I'm just tracking more stuff with less metadata now, right? I have a larger memory allocation, 2 megs, and I'm able to store a lot of data pages inside of there, right? So now, especially with what's going on with the new processor stuff, is we can reduce our TLB cache misses because we're going to be using larger pages, right? There's less stuff having to be able to move around inside of those page tables. Now, what this turns into for SQL Server on Linux, even before what's happening with the processor bugs, is this increases memory I/O by decreasing the number of TLB cache misses, right? And we'll be able to access this memory faster by allocating it in larger chunks. Now, SQL SV2, which is the thing that's in charge of resource allocation inside of SQL Server on Linux, can request large pages inside of SQL Server with the trace flag 834. So if I take 834 and allocate large pages inside of SQL Server, and I'm using transparent huge pages inside of Linux, which are enabled by default, you're going to get some pretty serious performance increases on scanning I/O, right? If you have a data warehouse workload or a large physically memory resident workload that's scanned frequently, this is a non-trivial amount of performance that you'll add to your system by enabling these 2 features. Again, your mileage may vary. Please test those things out. Now, what happens with when I turn on trace flag 834 is I have to allocate all the memory at the startup of the SQL Server process. We've probably seen that when we do that, when we enable that trace flag, because it's pre-allocating those large pages. But what's interesting is if you do this on a test machine, and this really kind of highlights a concept for SQL Server more so than it does the trace flag itself. SQLPAL only exposes 80% of the underlying physical memory on the system. So if I have an 8 gig VM and I want to test out this feature, well, what's going to happen is I'm going to start up my 8 gig VM, then SQL Server is going to start up, and SQL Server will only have about 6.6 gigs of memory exposed to it because SQLPAL only exposes by default the 80% of the physical memory on the system. You can change that in one of 2 ways. You can tell SQL Server with the mssql-conf command to allocate more memory to the SQLPAL, but that's only going to get you so far. Under the hood, though, we can just add more RAM to the VM, and it'll then be able to get us to where we need. So, that's why our test machine today has 11.6 gigs of RAM, so we're able to use this optimization. As of today, and last time I checked and validated this was in December, is we don't have locked pages. But what's interesting is, so we don't have locked pages of memory, so those things can be paged out. We're going to talk about that in a second. But if I run a query and I look at the execution plan and I look at the trace flags that are turned on during the execution, I see trace flag 835 is turned on, which is how we turn on locked pages in memory on standard edition. So now that we kind of have the theory of memory behind us, what do we want to look for inside of a Linux system? We want to look at high consumers of space, both physical and virtual. And is there a disconnect between those two? Do I have a lot of physical memory and a lot of virtual memory, or have a lot of virtual memory and a small amount of physical memory? If that's the case, if I have a lot of virtual and a small amount of physical, why? Why is the majority of my process not in memory anymore? And I want to understand what's going on there. We're going to look out for external memory pressure on SQL Server, right? We kind of alluded to this so far. Yes?
One question, my friend, is that the trace flag 834 is not recommended for column store indexes, and therefore Microsoft recommends to turn it off. Would that recommendation still be the same for SQL on Linux?
I would opt to say that if that's the recommendation on Windows, it's probably going to stand on SQL Server on Linux as well, because that's going to be essentially the same code that executes, because it's all going to be up inside of the database engine. So on SQL Server on Linux, what we have to understand is external memory pressure, right? There's no concept of resource monitor inside of SQL Server on Linux. On the Windows side of the house, we have resource monitor that says if there's external memory pressure on SQL Server on Windows, what will happen is the operating system will send a signal to SQL Server. SQL Server will dump its caches, buffer pool, plan cache, and things like that, and reduce its memory footprint and give those pages back to the operating system for the operating system to allocate them out to whomever else needs those. SQL Server on Linux doesn't have that, right? And we're going to show you in a few minutes is if I start up a process on a system that doesn't have a lot of memory to give, what will happen is the process address space or the virtual memory allocated to SQL Server on Linux will start swapping out the disk, and that can put us in a bad situation. And so we want to look out for external memory pressure on SQL Server. We also want to look out for any excessive swapping, and I'm going to show you how to identify these things in a second here. The tools that we're going to use for memory monitoring, well, we already know about /proc, right? Inside of /proc, there's a file called meminfo, which has the full accounting information for all the different types of memory allocations on our system. The primary tool for interrogating memory on our system is a tool called free. That's going to give us the total, the available, the allocated, and the size of our file system cache. We're going to use top and HTOP, which we looked at a few minutes ago. We saw that we had some memory information in there. PS is another good tool. And then VMstat and PIDstat shows up again. VMstat is going to tell me if my system is paging, right? I'm going to see things like page in and page out, right, for the allocation, deallocation of pages, and also block in and block out if I'm reading or writing pages off disk and pulling them back or pulling them back out. PIDstat is going to tell me which process. So VMstat will tell me if the system is paging. PIDstat will tell me which process is paging. And so let's go ahead and do that. We're going to look at memory layout. We're going to look at how to find a memory hog. We're going to look at how to identify external memory pressure. We're going to look at that together and also look at how to identify any excessive swapping. So let me bring up some stuff here. Okay, so far I showed you guys that we have a pretty big chunk of memory allocated. 8.93 gigs is allocated of 11.6, right? I have that 8 gig table loaded in, or the 9 gig table loaded into a SQL Server on Linux VM that has 8 gigs as the max memory, right? So the maximum amount of memory allocated inside of SQL Server is going to be 8 gigs. We go down here and we saw earlier, we see that we have a virtual address space of 10.4 gigs and our resident set size at about 8.7 gigs, right? So that's the physical amount of memory allocated to the process, the resident set size, and then the total VAS or the total virtual address space of 10.4. So we also looked at inside of here, we did PID of SQL Server, 1554. And we looked at status, all the different memory accounting information. So we looked at this a few minutes ago. We saw that our virtual address space peak is about 10 gigs. The peak amount of hard or resident set size memory or physical memory is 9 gigs, or right now a little bit below 9 gigs. And the majority of that is anonymous pages. So let's go and, oops, let me change that. I want to go into this one right here. Yeah, jumping around a second, clear my screen. Demos. I'm going to go in here. I have a program called memtest. What memtest will do is allocate the amount of memory that I pass as a parameter. So we see memtest 7000. That this process is going to do is allocate 7 gigs of contiguous memory, right? So SQL Server has us to the point where we're pretty close to the edge, right? We've got about 8.9 gigs of 11.6. So we still have a little bit of room, but I'm going to allocate 7 additional gigs of memory. So let's go ahead and run that. And so what's happening behind the scenes is allocating all those pages. So let's go ahead and look at what happens in HTOP. So what happens in HTOP is we see a whole bunch of red for each of the processes, right? This means this thing's going crazy inside of kernel space, allocating all the pages to support the thing that I'm asking it to do. We see that the physical memory in the system went from 8.9 to 11.3, right? So we're consuming as much physical memory as we can. A second ago, this swap file size was 0 gigs. Now it's 5.28. So 5.28 gigabytes of memory just got swapped out from primary memory to disk. Well, who do we think that was? If we go look in our list here, we can see SQL Server now has only 3454 allocated in physical memory. The virtual address space is still 10.4 gigs. It still thinks it has that much memory, but the back-end memory, about 5 gigs of that just got written out to a swap file. Now, what part of the process got written out to the swap file? Any part of the process. The majority of it did. More than 50% of the process did. Chances are the majority of that's going to be buffer pool, right? And so if I go and do a select star table, well, the weight stats that I get for that query are going to be weight stats that indicate that stuff came from primary memory, even though those backend pages are on disk.
Hey, Anthony.
Sir.
Somebody just asked if what was your min-max memory setting for the instance?
The min is 0. The max is 8 gigs.
Thank you.
Cool. Thank you. So now let's break out of here. VMstat 1. So here we can see right now there's not a lot of swapping going on because all that memory has been allocated. So we see swap in, swap out is pretty low, and block in, block out is pretty low, right? So really not a lot of data is moving around in our system. If I go here and I stop that process and I do a read table, this is going to go and read the table. I go back over here. Now we're going to see lots of swapping, right? We see swaps ins and swap outs, right? So we're basically moving things around. So what's happening is I'm reading that table contents, which is good, telling SQL Server to hit the buffer pool. The buffer pool is telling the process space, well, I need this memory location from your virtual address space. The operating system goes and gets a real page and then sticks the data that was swapped out the disk back into physical memory. And so it's going and moving all that stuff around. So my memtest process is now getting evacuated and pushed out the disk into the swap file while we pull back the buffer pool in. But right now you can't tell who, right, in that list. We just have a lot of data flowing around showing us that there are lots of swap in and swap outs are occurring. If I do a PID stat minus R, we'll see who, right? And we can see it's going to refresh every second. I'm going to get a couple samples here. We can see in our samples, we have SQL Server, right? Lots of minor faults, lots of major faults as it's increasing its resident set size. So if we follow this value over time, it's going to be getting larger from what happened a second ago. And we also see that the resident set size of our memtest program, I asked for 7 gigs, about 3 gigs is still in primary memory. So it's really doing a lot to move those things around to make sure that there is enough memory for our system. Another good way to see who was swapped out is if we go into proc 1554 and I go into status? Yeah, it's status. VM swap right here. This will tell us how much of the process address space is swapped out. So SQL Server still has about a gig that's sitting on the swap disk or swap file. So it's pretty nasty stuff if you run out of system memory. So what we did there, and let's kind of recap that, is we checked out the memory layout on the system, right? We saw we had about 11.6 gigs and about 8.9 allocated before we started the demo. Then we found that SQL Server was the big consumer of that. And then we started up a process that put a lot of external memory pressure on SQL Server on Linux, right? And then we saw what happened, right? SQL Server started to, or excuse me, the operating system started to page out big chunks of the process address space. And we used PIDstat and VMstat. VMstat showing us that there were lots of swap ins and swap outs occurring. PIDstat showing us which actual process was doing that heavy lifting. So let's move into the last big bucket of data, disks and file system. We're kind of in the home stretch, guys. So disks and file systems. If you just install Linux, specifically Red Hat, that's Red Hat or CentOS, the default file system that you're going to get is XFS, right? Another supported file system for SQL Server on Linux is ext4. Do I have a preference on which one? No. Honestly, whichever one is sufficient for your workload and validates in your testing is the file system that I would suggest to you. Block size is another common question that I always get about file systems on Linux, and which block size do I use? Well, really, the block size is going to have a nominal impact on utilization and performance nowadays, especially with modern disk arrays. The best answer I can give to you on which block size to use is to contact your storage vendor. They will probably have an opinion for you. The default block size on both of those file systems is 4K. One thing I do suggest you change, and the product team also suggests this as well in their best practices documentation, is to turn off the mount or use the mount time option no A time. What this does is inside of the file header metadata for a file is this thing called access time. And anytime the file is touched, that access time gets updated with a new value on the most recent access. If I have a bunch of threads concurrently accessing a file, which is the case in a relational database engine where I'm accessing one large file, this can become a performance bottleneck. And so one of the suggested things to do is to turn off that memory or that access time accounting with that no A time mount time option. Now let's talk a little bit about I/O under SQLPAL. And we looked at the two paths in the beginning of the session. We looked at there's two paths. There's the path that goes to the library OS or the NT usable kernel, and there's the path that goes through SQL SV2 and that performance sensitive path. And we're going to focus on the performance sensitive path and that fast I/O that occurs in the host extensions. There's this thing called kernel asynchronous I/O. What this does is it takes our I/O, it packages it up with a system call called I/O submit. That I/O submit then dispatches the I/O to the disk subsystem and does the work. What's interesting is this is asynchronous. So what happens is when I dispatch the disk I/O, the return of the code path immediately returns to the caller. So what happens is that thread state doesn't transition from running to sleeping because it immediately returns. And now that thread can go and do additional work and then pull the completion of that I/O completely in user space, right? So we're keeping that up in user space, even though we've just dispatched an I/O out to disk, which would conventionally transition us into kernel mode and transition us from a running state into a waiting state. And so that's one of the optimizations that we have to help us stay in user mode longer.
Hey, Anthony, we are well over the 120 also now, so I don't know how we want to handle that.
All right, we'll skip over a demo. So I'll go through this section here, and then we'll fly through a demo. I'll just talk kind of high level about that. So one of the other big optimizations that we have is this option for ODirect, which is the type of file mode that how we open up a database file, which bypasses the page cache. And that also helps I/O stay in user mode because when I/O is read off a disk, it's then delivered directly to the process. It's not handed off to a kernel mode buffer, and then the kernel mode buffer hands it off into user mode. So from a disk standpoint, what do we want to look for? We want to look for saturated disks and I/O subsystems. Really no different than what you're looking at in the Windows world. We really care a lot about swapping because that's going to put a lot of pressure on our disks. If we're out of memory, those things are all going to be pushed out the disk and putting a lot of pressure there. Caching is your friend, generally speaking. We talked about the file system cache, but not in a relational database engine, right? We want to adjust our swappiness. And also we know that ODirect disables caching, essentially the page cache for files when they're open with that option. But most importantly, we want a baseline. So from a demo standpoint or tooling standpoint, these are the big bucket tools that we want to use for monitoring. We need IOStat and IOTop, and also PIDStat, and then the Swiss Army knife DStat, which really helps us get good information out of that. I'm going to skip over this demo, but I do have the code, and I'll give the code to be published along with the presentation. But we would normally go through as we check some high I/O processes, and I'd also we go and we use it the conventional DMV, right? We still have that information available to us inside of Linux, so that's in the code that I'll give you guys as well. So the final section is monitoring tools, right? We're going to talk about baselining tools. Everything that we talked about so far, all the tools are based, I want to say micro benchmarks, but what happens on CPU, what happens on disk, what happens in memory? Well, there are two tools. We talked about DStat a lot already. There's another tool called SAR, the System Activity Reporter, which goes through and periodically collects system performance data over time and allows you to query a database to pull that information out so you can answer that question, what happened when? It goes through and collects all that data over time, and you can go and say what happened yesterday between time X and time Y using SAR. A really good utility there. We also have all the same tools that we have today, right? We have DMVs and extended events, so we can use those to query the information and the perf data that we are used to using inside of SQL Server. We obviously don't have perfmon data. That wouldn't be exposed because there's no underlying performance monitor inside of Linux. You do have the perfmon data that's SQL specific to SQL Server. You just don't have the perfmon data that's associated with the operating system. A bunch of other tools have come out along the way. There's a couple of new DMVs available to you guys. There is a PSS diag package that's available. You can check that out at that link there. DBFS gives you a procfs-like view into the DMVs instead of SQL Server. So I can go at the file system and I can interact with SQL Server and access DMV data externally from the file system. Good stuff there. The CAT team also put together some great performance visualizations with Grafana, so I strongly suggest you guys check out that information. The final thing I wanted to cover from a tech standpoint is metrics captured by PSS Diag. Well, all the stuff that we've been talking about today are the things that they use, right? CPU, disk memory, network, DMV data, and log information, and the tools that we talked about so far. These are all the things available inside of PSS Diag that go and collect that information. And so we covered a lot of turf. You know, I think we're over a little bit. We covered the Linux system architecture. We talked about SQL Server on Linux and the individual system components available, or the individual system components and the tools to monitor those. Then we zoomed out a little bit and looked at some monitoring packages. Things like SAR and Grafana are fantastic utilities to help you get things done. So like I said, I blog a lot. Check the blog out there. A couple of Pluralsight courses for you guys if you want to dive deeper into a lot of today's content. Those are much more deeper dives available to you guys. I also have some references here at the end. And so if you want to get into some more information, this fourth link here, I guess it would be the third link, the one that says Performance Tuning Guide from Red Hat, is fantastic. It tells you what attribute you want to tune, how to tune it, and the theory behind it. A great resource for you guys. So if there are any open questions, I'll take those now.
Okay, guys, so this sounds pretty cool. And I don't see any more questions. So people are looking happy here. So
cool.
Thank you, Anthony. I really appreciate that. I did actually tweet about it too. So
cool.
For
Thanks,
everybody on the call who is on Twitter, please go ahead and tweet about Anthony's awesome presentation. And there's like a ton of thank yous coming, my friend.
Cool. Appreciate everyone coming. Thank you guys for having me, of course. I really appreciate it.
Cool. Thank you, guys. Take care.
All right. Have a good afternoon, everyone. Thank you very much.